right? So welcome to this week's tutorial. So in this week, we will be covering exercise 11.1, 11.2, except 11.2.5, and exercise 11.3. So these exercises are basically based on graphs and trees. So we will be exploring some questions on those. And let's start with exercise 11.1. So for exercise 11.1, so this is the question 1. So we have to basically find out if these graphs are trees or not. So let's take part A here. So as we can see, this graph here can be basically, if we want to represent it as a tree, then we can, because every node is connected with an edge. So we can say that this graph is a tree. Part B. So part B here, because we have two nodes which are not connected by an edge, we say that this graph is not a tree. So part C is basically the same thing as part A. It's just that it's just overlapping over here, but it doesn't really matter. So it's the same thing as this. So therefore, we can say that this graph is a tree. Let's take part E here. So part E here. So we can see there is one node, and this node has 6 children. So 1, 2, 3, 4, 5, 6 children, right? So therefore, we can have a tree basically with a 1 parent node and 6 child nodes. So we can say that yes, this graph can be represented as a tree. Question? All right, no questions. Let's move on to the next one then. So we have this question number 3. So question number 3, part A. So we have this tree here. So we have to do, basically find out different things about the vertices. So we have to first find out which vertex is the root. The root vertex is basically like the top one, the parent node. So it is, in this case, the node A. Let's take part B. Part B, which vertices are internal? So internal vertices are A, B, C, D, F, H, J, Q, and T. So basically, internal nodes are those nodes which have a children, right? So we see that these nodes basically they have a children, so therefore they are internal nodes. Part C. Which vertices are leaves? So leaves, we know that E, G, E, G, I, K, L. This is I, K, L, M, N, O, P, R, S, U. So these ones are the vertices which are leaves. We have part D. Which vertices are children of J? So this is the vertex. So which vertices are children of J? So we have this Q and R as the children. So Q and R. Which part number E? Which vertex is the parent of H? Which vertex is the parent of H? So we have the vertex here, H. So C is the parent. F, which vertices are sibling of O? So sibling of O is this vertex P only. RG. Which vertices are ancestors of M? Now we are talking about ancestors and not just the parents. So we have to basically go towards the complete lineage. So we have F, B, and A. F, B, and A. Now, which vertices are descendant of B? So B here, so for the descendants of B, E, F, L, M, N. E, F, L, M, N. Right? Any questions here? Pretty straightforward question. Okay, if no question, let's move on to the next one. So how many edges does a tree with 10,000 vertices have? So we have a formula for calculating the edges. So this is basically E equals to N minus 1. Basically here E is the number of edges and N is the number of nodes. So here we have 10,000 nodes or vertices, 10,000 minus 1. So we get 99. So 9,999 nodes or 9,999 edges. Okay, next one. How many edges does a full binary tree with 1,000 internal vertices have? So since there are internal vertices 1,000 and we are supposed to find edges, since it's internal vertices, so we know that internal vertices are the one which has children. So, so therefore, it will be 2,000. Question number 27. Construct a complete binary tree of height 4 and a complete binary tree of height 3. Okay, so basically we have to construct binary trees here. Let me just stretch. So are you able to see the paint? Okay, so you can see both the paint and the word. Okay. All right, so basically we will draw the binary tree of height 4. So in this one here, we have So we will have one node which will have two children. So this is one node, this is the other node. This node, yeah, I'm drawing something. Are you able to see? Okay, let me see my settings. Right, are you able to see now? Okay, all right, so basically we're going to draw a binary tree of height 4. So we have this one root node, this is the other one, the second one, these are the two children's. This node will have two children's, and this node will have two children's. Furthermore, this node will have two children's, and this one will have two children's. This one will have two children's. This one will have two children's. So this is a binary tree of height 1, 2, 3. Okay. So now we basically have to draw a binary tree of height 4. We will basically add one more level to it. So we will have, this is a complete binary tree. Okay, so likewise, so this is the level 1, level 2, level 3, and level 4. So this is the height 4. So I'll just take this. Then I'll put it here. Okay, so basically this was a complete binary tree with height 4. Likewise, we can also do for the height 3. Okay, cool. All right, let's move on to the next one. So the next exercise we have is exercise 11.2. It's except 11.2.5, which we're not covering. And then it's available on page 805 of your textbook. So the first question is basically we have to build a binary search tree for the words banana, peach, apple, pear, coconut, mango, and papaya using an alphabetical order, right? So here we have okay. So we have banana, apple, peach, pear, coconut, mango, and papaya. So here we have so this one will be banana. This one will be apple. This node will be peach. This node will be coconut. And this node will be pear. This node will be mango. And this node will be papaya. So basically we have constructed in an alphabetical order. So we have banana here, and then because A comes before apple, so this is a binary search tree. So in binary search tree, we have the root. So the values on the left have the value is less than the root, and the values of the right have a value greater than root. So since P comes after B, so therefore we put it on the right, and A comes before B, therefore we put it on the left. Likewise, so we construct the same thing, and then we have this binary search tree. I'll just take this and just put it here. Okay, so this was the answer to this question. Next question. Any question here, by the way? All right, no question. Let's move on to the next one. So how many comparisons are needed to locate or to add each of these words in the search tree for exercise 1? Okay, so if we have to, for example, find the word pear in this tree, then how many comparisons will I need? So first of all, I will compare it with this. So this is comparison number 1. So I know that pear is greater than banana, right? Because P is greater than B. B comes after B. So this is one comparison. So therefore, I will move to this node here. So the second comparison will be this one here. Is peach this the pear? If not, then I move on to the next one. So this is pear. So I search for this node. Is this pear? Then I find that this is pear. So therefore, this is 3 comparisons. Okay. 3 comparisons. Part B. Part B. Okay, so we have to find the word banana in this tree. So since banana is the root level element, so therefore once we come to the root, we start with the root and then we search for if this is banana, we see that this is banana. So therefore it only requires one comparison. Part C. So we have this word kumquat. And we search for this in the tree here. So we have to find how many comparisons are needed here, or if I want to insert this. So first comparison is, so I will compare it with this word banana here. So now because a K comes after B, so I will move down to this. Now, so this is my second comparison. Is peach kumquat? It's not. Since K comes before P, I'll move down to this. So now we have already done 2. Okay. Now C. C, is C kumquat? No. So we move down to this node. Now we are 3 already. So now I search for is kumquat mango? No, it's not mango. But since so so K comes before M, so therefore I will put it here, over here, if I have better. So that will be my 4th comparison, right? So therefore 4 comparisons are needed to add this word, kumquat. Now the word orange. I have to look for the word orange in this, or if I have to add it. Now I will, first of all, I will start with banana, of course. So is banana orange? No, it's not. So this is one comparison. The second one will be with this peach here. So is peach an orange? It's not. But where should we go? So we basically see, does P comes before O or O comes before P? So O comes before P, right? So we will come down here, right? So I'll make a comparison with C. So C, so this is my third comparison. So is coconut an orange or not? It is not. So therefore I'll come down here, right? Now, because mango is also not an orange, I will come down here to papaya. So this is my fifth comparison. If I take this route 1, 2, 3, 4, 5. And now if I have to add an orange, I can basically make it a left child of papaya. So in total, we had to make around 5 comparisons to basically add the word orange. Great. Any questions here? All right. If no question, let's move on to the next one. So we have to basically construct a binary search tree for the words in the sentence. The quick brown fox jumps over the lazy dog. Okay. So now we have to start with the word the. Okay. Right, so the word the. Now Q, because Q is here. Q comes before T, right? So we will take this path, right? The quick. So this node will be the, and this node will be quick. Now B comes before B, quick. So therefore we will take this path. Now fox comes after brown. So we will take this path. And then dog comes before fox. We'll take this path. Jumps. And then we have the over. Lazy. Okay, so let's give them the node names. So this node will be the, and this node will be quick. The quick, this node will be the quick brown fox. Fox jumps over, but the is already here, so we want the lazy dog. Okay, so here we have the quick brown fox jumps over the lazy dog. Let me take this and then I'll put it here. Okay, so basically what we had to do is we had to sort of make comparison in the alphabetical order, right? In alphabetical order. So we have to see which letter comes before the first one, or which alphabet comes before the first, the previous one. And based on that path, we will construct our binary search tree. Any questions here? Okay, all right. Let's move on to the next one. So we have this question number 21. We have to basically what are the codes for these A, E, I, K, O, P, and U if the coding scheme is represented by this string. Okay. So we have to find the word for the word A, for the letter A here. We have to find out the code for it. So for example, how many digits or what's the pattern of digits I need to basically represent this letter A with. So I will start from this. I know I have to get here. So I will take 0, 0, 0. So 0, 0, 0 will be the pattern for word A. Just put it in like this form. A. For letter E, so I will say 0, 0, 1. 0, 0, 1. 0, 0, 1. Letter I. So I have 0, 1. I, and then I have K. So I have 1, 1, 0, 0. 1, 1, 0, 0. And then I have O. O can be 1, 1, 0, 1. 1, 1, 0, 1. O, P. P can be represented using 1, 1, 1, 1, 0. 1, 1, 1, 1, 0. U can be represented with 1, 1, 1, 1, 1. 1, 1, 1, 1, 1. Okay. So basically just following the path that reaches that node starting from the root and then collecting the digits across the way. Any questions here? All right, if no question, let's move on to the next exercise. So the next exercise is basically exercise 11.3. So in 11.3, what we have to do is we have to determine the order in which a pre-ordered traversal visits the vertices of the given ordered rooted tree. We have to basically do a pre-order traversal. So in the pre-order traversal, we visit the root, and then we visit the left, and then we visit the right child. Okay. So having that in mind, I can maybe we'll do it over here. Okay, so let's take question number 7. So question number 7, I will visit this node first, so A, and then I will visit question number 7. So A, and then I will visit the left child, B, of this node, and then I will visit its left child, D, and then I will go to E, to the right side, E here, and then I will visit its left, F, and then its right is G, and then this node here, which is C. All right, let's take another example. Question number 9, a little bit complicated. Okay. So question number 9 here, I have to do the pre-order, right? Okay. So here I will visit node A first, and then I will visit this B, and then I will visit this E, K, E, K, and then I will visit, it's right, L, and then this M, L, M, and then this F, G, N, F, G, N, and then this R, S, and then I'll move on to this subtree, C, and then this one D, H, O, I, J, P, Q, I, J, I, J, P, Q. Okay. So in that fashion, we will basically doing the traversing, the pre-order traversal of these trees. I'll just take this. And I'll put it here. Okay, questions here. All right, no question. Let's move on to the next one. So question number 17. So question number 17 asks us to do traversing on these. So represent the expression this and this using binary trees to write these expressions in prefix annotation. So, okay, so let's do the A part. So A part we have so we will only be doing let's say this expression. So we have the plus here in the middle, so plus. So we will have this plus which has two subchildren. So this will be the plus in the middle, and then this will be the left subtree, this is the right subtree. This will be the division branch, this is X and this is Y. And this is the addition branch, this is X, and this is the multiplication branch. This is X and this is Y. Okay, so let's put on some text here. So this is the plus sign here. The plus sign, this plus sign, and then we have this plus sign here, plus, and then we have this X here, X, then we have this another X here, we have a Y here, then we have the multiplication sign because of this XY, this is multiplication, so I'll put multiplication sign here. This is the division sign here. And then we have X, then we have a Y. A Y here, and we have the X here. Okay. So basically this expression here can be represented using binary tree, using this binary tree here. So I'll just take this. And then I'll put it here. So this is the binary tree equivalent of this expression. The next one is write these expression in prefix notation. So I will take so I will have to do the prefix notation or the prefix traversal of this tree now. So B part. So prefix basically says that you have to, like previously how we did, we have to visit the root first and then left child and then right child. So if we visit the root, so this is plus plus x plus plus x, and then we have this multiply x y, multiply x y, and then we have this division x y, this division x and y. Now we have to do the postfix traversal. So postfix, basically you have to visit the left child, the right child, and then the root. So left child will be this x, and then this x here, and then I will visit the right child y, and then I will visit the root multiply, and then this root plus. And then this x, y division plus, x, y division plus. The next part basically asks us to do the infix notation. Infix, you visit the left child, you visit the root, and then you visit the right child. So the infix notation is so I visit the left child, this x, and then I visit the root plus, and then I visit this left child here, x, then I visit the root multiply, and then this right child, y, and then I visit this plus here, and then I visit this x here, this division, and then this y here. Okay, so this is how you do the prefix traversal, postfix traversal, and infix traversal of the different fields. Any questions here? Right, if no question, let's move on to the next one. So basically the next one is, so in the next one, we have question number 31. So show that any well-formed formula in prefix notation over a set of symbols and a set of binary operators contains exactly one more symbol than the number of operators. So for this formula, for this proof, we will be using the mathematical induction. So we will be proving this by mathematical induction. So this will be approved by mathematical mathematical induction. So we will say let S of x and O of x represent the number of symbols and number of operators in the well-formed formula X respectively. So here Sx represents the symbols in the well-formed formula X, and then O represent operators in this well-formed formula. Okay. Now this statement this is like the basic step. So the well-formed formula, the simple one is of length 1. So therefore, the basic step will involve for length 1. So the statement is true for well-formed formula of length 1 because they have one symbol and 0 operators, right? So because this is a simple one, it only has one symbol. It doesn't have any operator. So therefore, it is a well-formed formula. Now, inductive step. So now in the inductive step, we assume the statement is true for all well-formed formula of length less than n. Okay, so we are basically assuming that this is true for all formula that whose length is less than n. Okay. A well-formed formula of length n must be of the form multiply xy. So some operator where x is an operator, this multiply sign is an operator, and x and y are well-formed formula of length less than n. Okay, great. So then by inductive hypothesis. So basically what we did here is that in the inductive step, we assume that it is true for this is a well-formed formula of length that is less than n. And then we have to prove it for the length n plus 1. So here we have this operator. It can be any operator, and then these x, y are basically the symbols of some well-formed formula of length less than 1. Okay, so then by inductive step, we have to now do the inductive step. So we say that this, so this operator s equals to s x plus s y. Okay, so this is equals to this, and this is equals to O of x plus 1 plus this is the operator y plus 1. This is equals to O of x plus O of y plus 2. Now, because O multiply xy equals to 1 plus O of x plus y, it follows that s multiplied by xy equals to O multiplied by xy plus 1. Okay. So now we have proved it for values just for s plus 1. So therefore we can say that hence proved by mathematical induction. Right. So basically what we did is, we had to prove that any welfare formula in prefix notation over a set of symbols and a set of binary operators contain exactly one more symbol than the number of operators. So here we have basically proved it by mathematical induction. We did the basic steps. So in the very basic step, in the very basic well-formed formula, we have just one symbol and we don't have any operators. So it is the well-formed formula of length 1. For that formula, we basically had uh, so it will be just as simple as this s of x, where x is any symbol, right? So this is like the most simplest Wolfram formula of length 1. So this is a basic step, and this holds for this statement, right? Because it doesn't have an operator, it has one symbol, which is more than one operator, right? So the next step will be the inductive hypothesis. In the inductive step, what we did is we assumed that it is true for length n, and then we have to prove that it is also true for n plus 1. So now what we did is we have this well-formed formula of length n must be of the form xy, right? So it is a multiplicative of this form, right? So this is an operator, and x and y are well-formed formula of length n. So now we performed our inductive hypothesis step. So s multiplied by xy equals to sx plus sy. Now we have this operator of x plus 1 plus operator of y plus 1, right? So this the symbols xy can be basically split over in this. And then they are equivalent to operator of x plus 1 and then operator of y plus 1, right? Which is operator of x plus operator of y plus 2. Okay. Now, because operator of x, y, this operator plus equals to 1 plus operator of x, operator y, it follows that s xy equals to o xy plus 1. So therefore, we have to prove it by mathematical induction that any well-formed formula in prefix notation over a set of symbols in a set of binary operators contains exactly one more symbol than the number of operators. Okay, any questions here? All right. If no questions here, then that is pretty much it for this tutorial. And I will see you guys in the next tutorial. And yep, so that'll be pretty much it for this tutorial. And yeah, have a good evening. And I'll see you guys in the next tutorial. Take care.